Hello and welcome to the continuing videos in the linear algebra series. So in this video, it's actually going to be a pretty quick one. I just want to talk about a few more results in terms of the stuff that we've been talking about. So far in these videos, we've been seeing a lot of two separate ideas: matrices and their operations, systems of linear equations. And while we have talked about elementary matrices a little bit and how they gave us a method for finding the inverse in using row reduction, there hasn't been a lot of connection between the two. So the purpose of this video is to kind of just add in a few more gaps that are missing there and a few more properties. So what you're seeing right in front of you should look somewhat familiar. And this was a few properties that were equivalent, namely A being invertible, only having the trivial solution to AX equals 0. The reduced row echelon form of A is just the identity, and A is a product of elementary matrices. But there's a few more properties that should seem like they happen at the exact same time. So specifically, in terms of a couple more types. So this is going to look a little bit more like what we're dealing with B. So this was an example of a homogeneous system of equations. Again, just for a bit of a reminder that any system of equations can be written in matrix multiplication form. We would have seen a previous video on that. But it's quite special that we're dealing with zeros on the other side. What if we aren't dealing with a homogeneous system of equations? What if there's actually numbers there that aren't all equal to 0? Fortunately, we can add a couple more properties to our list. So AX equals to B. And both of them are actually going to be talking about B. In terms of how many solutions would these have? And the idea is, well, if A is invertible, it should be fairly easy, assuming we knew the inverse and we have a method for finding the inverse, it would be fairly simple in order to actually solve this. If AX is equal to B and A inverse exists, then what happens when you're actually solving for X? Well, X would be equal to A inverse times B. Now that doesn't prove that they're equivalent, because that's only one direction, but it hopefully gives a little bit of an idea as to what we get when we complete this right here. So first of all, is there going to be a solution? Well, we just saw that it is. So AX equals B is consistent for any n by 1 matrix B. Again, A is a square matrix. Let's say it's an n by n matrix. So it's consistent. So consistent would mean it has a solution. There is always a solution. But we can say even more than that, that AX equals B has exactly one solution for any n by 1 matrix B. And so we actually have more of a connection between a system of equations, and E and F are about systems of equations and properties of matrices, specifically the coefficient matrix of that system. So if you have a system of equations, for example, x plus y equals 5, and x plus 2y equals 7, then the matrix A we're talking about is 1, 1, 1, 2. And the fact that this matrix has an inverse And we know that because 1 times 2 minus 1 times 1 is non-zero. We had a rule for 2 by 2 matrices. The fact that this matrix is invertible tells us that this system has a solution and has exactly one solution if I replace 5 and 7 with 3 and 10. If I replace them with negative pi and pi to the e. If we replace them, if you're comfortable with complex numbers, if you replace them with complex numbers. That this system will always have one and exactly one solution. And that's what these other properties are. Which naturally leads to a question that we discussed probably in the very first video on systems of equations, namely one more property. Every system AX equals B has either no solution, one solution, or infinitely many. Which again, probably not something that's overly surprising. We would have seen that in our row operations in terms of actually solving them. If you get a row of zeros with a non-zero in the augmented part, that means there's no solution. If there's a column in every, or a leading one in every column, you get exactly one solution. If the system is consistent, but there's a column without a leading one, you get infinitely many. So this, while we may not have written it down, was not a property that's overly surprising. Okay. So that's it for this video, just plugging in some gaps in some of our rules, our consistency, and a couple more things in our list of equivalent statements. And just to reaffirm what this really means is that when I say all these are equivalent, that would mean if you had a matrix A, and if one of these properties are true, then all of these properties are true. If one of these properties is false, then all of these properties is false. In other words, if the reduced row echelon form of A is not I, then all of these statements are false. But I do want to be careful with E and F when I'm talking about it being false. So if the reduced row echelon form of A was not I, in other words, A is not invertible, feel free to ask yourself, what would that mean for this statement here to be false? So what it means for E to be false does not mean that it's inconsistent for every matrix B. For example, AX equals 0 always has a solution, the trivial solution. So what E being false would mean is that it is going to be consistent for some matrices, but not all. So if these are all false, because the reduced row echelon form is not the identity, that would mean that while this system is consistent for some matrices B, just not all of them. For F, similar idea. So what that would mean is that it does not have exactly one solution for all of them. Now, as it turns out, it would mean that it either has no solution or infinitely many. But what this is saying is that, again, we can't say it's true for all, even though it might be true for some. All right, anyway, so that's it for this video. See you in the next one.